Content in this presentation is covered on pages 222 through 225 of your textbook, and it's meant to help you achieve learning objective number 37, which is to describe the airflow around a low pressure center or a cyclone, and also around a high pressure center or an anticyclone, and also to be able to describe the weather associated with both of those systems. Be sure to skim those pages before you watch the video and read the chapter carefully before you attempt any of the online quizzes. So far, we've discussed wind without regard to how airflow in one region might affect airflow elsewhere. Although the butterfly flapping its wing analogy, where the butterfly flaps its wings in South America and as a result a tornado forms in the United States, that's an exaggeration. But it does suggest that airflow in one region might cause a change in weather at some later time at a different location. So just how horizontal airflow or wind relates to vertical flow, that's an important issue. Although the rate at which air ascends or descends, except in violent storms, is slow compared to horizontal flow, it's very important as a weather maker. So you learned earlier in this course that rising air is associated with cloudy conditions and often precipitation. You also learned that subsidence produces adiabatic heating and clearing conditions. In this section, we're going to talk a little bit about how the movement of air can create pressure changes and hence generate winds. So there are not many slides in this presentation, but they are meaty. They're sort of densely packed with information. Look for a minute here at these two pictures. Both are low pressure centers. One is in the northern hemisphere, the other one is in the southern hemisphere. Can you figure out which one is which? The one on the left is the northern hemisphere. It is a large low pressure center in the Gulf of Alaska. The cloud pattern shows an inward counterclockwise spiral. That counterclockwise direction is your clue that the storm is in the northern hemisphere. The clouds themselves tell you that the flow is cyclonic in nature. If this were an anticyclone, we would have no clouds, right? We only have clouds when we have rising air, like around a low pressure center. Anticyclonic flow, clear skies. The storm on the right is the southern hemisphere, and you can tell that because the inward spirals clockwise. Surface low pressure systems, or cyclones, all have that inward spiral. This transport of air towards the middle causes a shrinking of the area that it occupies. That's a process called convergence. And whenever air converges horizontally, it piles up. So it's increasing in mass to allow for the decreased area that it occupies. And that generates a denser column, which in turn ultimately generates higher pressure. And so these are, while they're interesting and significant storm systems, they're very short-lived. We've encountered this paradox here. Low pressure centers cause a net accumulation of air, which increases pressure, and consequently a surface cyclone should quickly eradicate itself. You can see that for a surface low to exist for a substantial duration, there has to be compensation aloft. For example, a surface convergence could be maintained if divergence occurs aloft at a rate equal to the inflow below. So this figure illustrates the relationship between surface convergence, inflow, and the divergence aloft, or outflow, needed to maintain a low pressure center. Divergence aloft may even exceed the surface convergence, thereby accelerating the vertical motion and intensifying the surface inflow. Because rising air often results in cloud formation and precipitation, the passage of a low pressure center is generally accompanied by what we call bad weather. Like their cyclonic counterparts, anticyclones must also be maintained from the above. Outflow near the surface is accompanied by convergence aloft and general subsidence of the air column. Because that descending air is compressed and warmed, cloud formation and precipitation are less likely in an anticyclone. So fair weather can usually be expected with the approach of a high pressure system. In this model, you can see how the upper atmosphere pressure conditions are expressed by the patterns of wind direction aloft. Convergence aloft occurs where the skies are clearing in the high pressure regions, and it's likely that the isobars, or pressure surface isolines, will be bunched together between the anticyclonic system and the cyclonic one further to the east. The steep pressure gradient means that the winds aloft will be fastest where the isobars, which are represented by the big blue arrows, are bunched together. For these reasons, it's common to see stormy at the low pressure end of household barometers and fair at the high end. By noting the pressure trend, rising, falling, or steady, we have a good indication of forthcoming weather. Such a determination, called the pressure tendency or barometric tendency, is very useful in short-range weather prediction. This, by the way, is why local television weather broadcasters emphasize the positions and projected paths of cyclones and anticyclones. Lows move in roughly a west to east direction across the United States and require a few days to maybe sometimes more than a week to make that journey. Because their paths can be erratic, accurate prediction of their migration is difficult. Yet it's essential for short-range forecasting. So meteorologists must also determine whether the flow aloft will intensify an embryo storm or suppress its development. Because of the close tie between vertical motion in the atmosphere and daily weather, we'll consider some other factors that contribute to surface convergence and surface divergence. Friction can cause both convergence and divergence when air moves from the relatively smooth ocean surface to land. For instance, the increased friction causes an abrupt drop in wind speed, and that reduction of wind speed results in a pileup of air upstream. So converging winds and ascending air accompany flow from the ocean to the land. This contributes to the cloudy conditions over the humid coastal regions of Florida. Conversely, when air moves from land to the ocean, general divergence and subsidence accompany the seaward flow of air because lower friction and increasing wind speed over the water. The result is often subsidence and clearing conditions. So mountains too can hinder the flow of air and cause divergence or convergence. As air passes over a mountain range, it's compressed vertically, pushed upward, which produces horizontal spreading aloft. After reaching the leeward side of the mountain, that air parcel experiences a vertical expansion. It stretches, which causes convergence aloft. So that effect greatly affects the weather in the United States east of the Rocky Mountains, as we'll see later on. The connection between surface conditions and conditions aloft have led to a significant study of atmospheric circulation, especially in the mid-latitudes. So use the course content provided on the Canvas site, as well as outside internet sources, to verify that you can formulate answers to these questions. If you can comfortably answer them, you're in great shape. If you can't, review the textbook, rewatch the video, and see if your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.